Hello and welcome. Today we're going to be looking at 2012, the AP Chemistry exam, the first question. We're going to be looking through this entire pre-response question, going through it so that you understand how to approach these questions and are ready to ace the AP Chemistry exam. If you like these videos or find them informative, please be sure to like and subscribe. And with that, let's get started on these questions. Alright, number one. A 1.22 gram sample of a pure monoprotic acid, HA, was dissolved in distilled water. The HA solution was then titrated with 0.250 molar sodium hydroxide. The pH was measured throughout the titration, and the equivalence point was reached when 40 milliliters of the NaOH solution had been added. The data from the titration are recorded in the table below. And we're given that this table, a volume of the sodium hydroxide added versus pH titrated solution, and we have to explain how the data provided in the table provide evidence that HA is a weak acid rather than a strong acid. Alright, let's see. How are we going to go about doing this question? Alright. Well, let's see. Make a text box and start thinking out loud to see what we can hit with this. Well, at the equivalence point, which we're told is at 40 milliliters, the pH is 8.62, right? So since, or at the equivalence point, all of the acid has reacted with the sodium hydroxide, and all that is left is the conjugate base. Since the conjugate base raises the pH a significant amount, conjugate base raises the pH a significant amount, it is a weak base. The conjugate of a weak base is a weak acid. So HA is a weak acid. And that's why. Let's move on to the next part. Alright, we have part B. And we're told to write the balanced net ionic equation for the reaction that occurs when the solution of NaOH is added to the solution of HA. So we know that the NaOH is going to completely dissociate. The HA will not completely dissociate. And we know that the Na plus is going to be, well, it's a group 1 salt, so it's going to always be soluble, and we can just leave it out. So we can take OH minus plus the HA, and that becomes H2O, the water, plus A minus, the conjugate base. And that's our net ionic equation. Let's move on to the next part. Alright, next part is what? Calculate the number of moles of HA that were titrated. Well, the equivalence point was at 40 milliliters, so we have 40 milliliters, or 40 times 10 to the negative 3 liters, times 0.250 molar is going to be, if we can pull out our calculator, we get 40 times 10 to the negative third times 0.250 is going to be 0.01 moles of sodium hydroxide that was added. And the equivalence point means that the moles are going to be the same for both of them. So our answer is going to be 0.01 of HA that was titrated. And we can move on to the next part. Alright, next part, here it is. Calculate the molar mass of HA. Well, 0.01 moles and it's 1.22 grams. So we just take that 1.22 grams, we divide that by the number of moles, that is 0.01 moles, and we get 122 grams per mole as our molar mass. That is our molar mass. And we can move on to the next part. Alright, part E. It says the equation for the dissociation reaction of HA and water is shown below. So we have HA plus water is in equilibrium with hydronium plus conjugate base. The Ka is 6.3 times 10 to the negative 5. And we're going to assume that the initial concentration of the HA solution before any NaOH solution was added is 0.2 molar. Determine the pH of the initial HA solution. Alright, let's see how we're going to go about doing this question. Well, the equilibrium expression here, right? The equilibrium expression here is going to be, we have Ka equals, on the numerator we have the concentration of the H plus, the protons flying around, and the conjugate at the base. And then the denominator we just have HA, because the water is not going to be in there. So if we set H plus as X, well, H plus and A minus are going to be the same. Concentration is going to be the same. Since for each H plus we create one A minus. That's going to be equal to X. And then we know that HA starts at 0.2 molar, so that's going to be 0.2 minus X. And then our equilibrium expression, our Ka, which remember they told us is going to be 6.3 times 10 to the negative 5th, is going to be x squared times 0.2 minus x. And we can solve this, and we get x equals, right, so let's bust out the calculator, and we get and for our answer for our x, we get that the answer is going to be 0.0035. Alright, that is going to be our answer. So if you're wondering how I did this, I did not use the quadratic formula. That's much too tedious. What I really did is I just plugged in, as for y1, I put in, I don't know if you can see that, I put in 6.3 times 10 to the negative 5th as y1, and as for y2, I put in x squared over 0.2 minus. Essentially what I did here is I set these two parts as equations, and then hit the graph button, and then use the calculate intersect function to put these two together. Now that is one way of doing it that doesn't use the quadratic formula. There is another way to do this that only works sometimes, but it always works. Like usually works, right? Because College Board doesn't like to make you do the quadratic formula. So in this scenario, we can assume that x is much less than 0.2, and therefore x is negligible compared to 0.2, and we can just write 0.2 in the denominator. And then we end up with 6.3 times 10 to the negative 5 times 0.2 equals x squared. And we take the square root, and here we get, for this one that we tried, we get 0.00355 instead of what before was 0.00351. Alright, so as you can see, the assumption doesn't really change that much. It still works either way, right? But here x is going to be 0.0035. Now we still haven't answered the question, Right, they asked us for the pH of the initial solution. Right, we still haven't found the pH. We just found the concentration of hydronium of the H plus. And how is that helpful? Well, if you remember, pH is just going to be the negative log of H plus negative log of 0.0035 equals, let's press out our calculator again, and we get the negative log 0.35 is going to be 2.46, rounding to our number, not rounding to our 3 decimal places. We get 2.4, actually 2.45, not 2.546. It's not 2.46, 2.45. 2.45, right? This is why you use the log of whatever you got as the graph instead of what just the 0.0035. And our answer for our pH is going to be 2.45. That is the pH of the initial solution. All right, and then for part F, we're now asked for the value of the concentration of hydronium in a solution after 30 milliliters of NaOH solution is added, and the total volume is 80 milliliters. Let's see what we can do here. So after 30 milliliters are added, and the total volume is 80 milliliters, so we started with 50 milliliters, right? Started with 50 milliliters, and started with 50 milliliters. Make a text box so we can write down what we're thinking. So we started at 50 ml. NaOH is 30 ml. So we still have how much? Well, we know from before that we have 0.01 moles of HA. Right? We have 0.01 moles of HA. And what else do we know? We know that we've added 30 milliliters of NaOH, which is going to be 3/4, so which is 3/4 of the total amount necessary to get to the equivalence point. Essentially, we've used up 3/4 of the number of moles. So we have neutralized 3/4 of the number of moles to 0.01. So we have 0.00 or 0.0025 mole remaining. Now, of course, you don't need to write down this explanation, right? They're not asking for an explanation. I'm just doing this because it's helping me visualize what's going on, right? It's kind of like how in some quests you might do a setup. This is kind of my setup in my head, just what is going on, right? Instead of having to put this all in my head, I'm writing it down so I understand, well, how to get from each step to the next step, and how to get that gives me a clear pathway to the answer, and I make sure I'm not messing up any place carelessly. I'm not making an arithmetic error or something. But now we found that we have 0.0025 moles remaining of H plus, right? So we have 0.0025 moles remaining, and we have 80 milliliters in solution. So our molarity is going to be equal to 0.0. It's going to equal to 0.0025 moles. The denominator is going to be 80 times 10 to the negative 3 liters, right? Since we have 80 milliliters, we have 80 times 10 to the negative 3 liters. We're going to put that in here at 0.025 divided by 0.08, which is going to be 0.3125 the two significant figures, it's going to be 0.31 molar, and that is our initial concentration of hydronium in the solution after 30 milliliters of NaOH solution is added, and the total volume of solution is 80 milliliters. Or is it? Right, we went through this whole process, and this is why you have to write things down. Right, if you hadn't wrote this down, you wouldn't have caught this error, right? Because the error here is that we assumed that all of the all of the H plus, all of the hydronium would come from the HA. We assumed that the HA would completely dissociate, and that would give us the same number of moles of hydronium as we originally had, which is not true. That's not what's happening here. We have to rethink it. Right? This is why you write stuff down. Right? So let's think about this again. Right? This way, since we know what we've done, we can think about this again. So we have neutralized this 0.01 3/4 of the moles, so we have 0.0025 mole remaining of the HA. Well, how does that help us? Let's think about it differently. Right? How many moles of hydronium did we have in the initial solution? Well, we can go back to part E, and we can see here that X is going to be 0.0035. That's our initial molarity. So we have that 0.0035 molarity. Let's put that in an equation. 0.0035 molarity times, well, how much solution do we have right here? We have what? Well, we are in the initial HA solution, which is 50 milliliters, right? Since we're told that after the 30 milliliters added, we have 80 milliliters total. So we have 50 times 10 to the negative third liters. So we multiply that all together, and we get 1.75 times 10 to the negative 4 in moles. All right, so that's how much we have for the number of moles of the HA. All right, so essentially that's how much hydronium we have. That's how much of the actual HA we have. Right? Now, what are we going to do now? Well, could we just divide it by 4 and try that? Well, would that work? Well, it doesn't seem like it would work, right? Because when you're adding the NaOH, the equilibrium is going to change, right? So this is not going to work, and we have to go back to the drawing board and start thinking about this again. Let's just get rid of everything with the clear head and think about how we're going to go and do this problem, right? What we're going to do in this problem to get what we need. All right, so what do we have? What do we have to start with? Well, we can write some things from before and after the reaction. Right, this is where we use our ice boxes. I know we've been skipping using the ice boxes in the past couple things because after you've used these ice boxes enough, you don't even need the ice box anymore. You can just assign the x values. But here we're going to actually make an icebox because it is going to be helpful for us. All right, so we have four different parts of this equation. Right, so we're going to do 5 different things. We have this. I don't know why it's giving me a bunch of colors. I didn't really want the colors, so I'll just write before reaction, after reaction, and this is going to be the HA, H plus, or oh, actually, no, this is H2O, 2O. This is the H3O, O plus, and this is the A minus. And then, of course, we can add a cell to the left, insert columns to the right, and that's going to be our arrow. Right? And of course it goes in both ways since this is equilibrium. No, I don't know why this is happening. Not my fault. Alright, so now what can we do? What can we do with this icebox that we have here? Well, what do we know before the reaction? We know that before the reaction, the HA is going to be what? Well, before the reaction, how many moles of HA did we have? Right? Before the reaction, we had 0.01 moles of HA. Right? We had 0.01 moles of HA. And how much A did we have? 0 moles. And now what? Now how do we go about doing this question? Well, let's see. So does this seem like the right equation now? Right? Are we really trying to create the H3O plus? This is another place where you have to be careful with this, right? We took the equation that they provided for the dissociation reaction, but that's not what we're using for the titration, because we're adding NaOH, so we're adding the OH. We're not adding this water, we're adding OH minus. And this right here is going to be our H2O, H2O, which of course means that this is not going to be useful at all. We're not going to be using this, right? Oops. Not going to be using that part. And so we had 0.01 moles and we had 0 moles of A minus. How much OH minus did we have before the reaction? Let's think about that. So before the reaction, before we basically reacted all of this hydronium and the NaOH and everything, well, we added 30 milliliters, which is 3/4 of our total. So we're going to have 0.0075 moles, right? 3/4, so 0.0075 moles. Now what's going to happen after the reaction? Well, we're going to react all of this down, so this is going to become 0 moles. We're going to react 3/4 of this, so we just end up with 0.0025 moles. And then over here, we end up with 0.0075 moles, the amount that was reacted. And that's what our icebox is going to look at. That's what our icebox is going to look like at the end. And now what do we do? Well, this is what kind of equation, right? Now how do we use this equation? Let's see. So we know a couple things, right? We know we have a Ka expression. Right? We know the Ka expression is Ka, which, you know what, I really should not write that. I'll just write it in text box. We have that Ka equals what? Well, it's going to equal the H plus times the A minus over the HA. And well, why are we using this? Why are we using this right now? We're not even using that equation that corresponds with this. Well, the reason we're using this is because this gives us a way to figure out the H plus value, since we know what the Ka is. We just need to find the concentration of A minus and the concentration of HA. And lucky for us, we have values for those because we have an amount of moles. In the solution for each of these, and so we have an amount of moles. We have an amount of volume, the 80 milliliters. Let's go plug and chug, figure out what we can do here. So we have HA equals 0.0025 moles over the 80 times 10 to the negative 3 liters. And let's see, let's open up our calculator. And we get 0.031, which is also known as 3.1 times 10 to the negative 2, negative 2. molar, right? And that's our concentration of HA. And then we do the same thing for the A minus, and really we're just going to get the same thing but 3 times as much. And so we have A minus equals 0.0075 moles times over 80 times 10 to the negative 3 liters. That's going to be equal to, that is going to be equal to 9.4 times 10 to the negative 2 molar. And that's going to be our HA and our A minus, right? So now what do we do? Well, now we know that this is our K expression, so we can plug in a couple of things. We know that A minus over HA, well, A minus is 3 times that of HA, so this is really just going to be 6.3 times 10 to the negative 5th equals 3 times H plus, concentration of H plus. So H plus is going to be equal to 2.1 times 10 to the negative 5. 2.1 times 10 to the negative 5 molar. Not that, molar. And that is going to be the value of the concentrated hydronium in the solution after the 30 milliliters of NaOH is added and the total volume is 80 milliliters. As you can see here, it's always important to write down what you're thinking, even if they don't ask you to explain. Put down the setup, get the setup points if there is any, even if there's not. It'll help you visualize what's going on, it'll help you catch mistakes, it'll help you find a clear pathway to the answer. And now we found our answer, 2.1 times 10 to the negative 5 molar. That is it for this question, and I'll see you next time when we continue looking at more AP Chemistry FRQs.